Hello everyone and welcome to this video on the role of digital electronics in quantum computing. We are living in a time where technology is evolving faster than ever before, and right at the edge of this evolution lies quantum computing. It promises to solve problems that even the world's fastest supercomputers can't handle efficiently. But have you ever wondered what actually makes a quantum computer work? Well, we often hear about the things like qubits, entanglement, and superposition. There's a silent partner that's just as important, digital electronics. In this video, we'll explore how classical digital components like logic circuits, microphones, microcontrollers, signal processors are not just supporting the quantum computers but are absolutely essential to make them work. So, whether you are into physics, electronics, or just curious about the future of quantum computing, stick around as this video is going to help you a lot. Before we talk about how digital electronics helps quantum computers, let's understand what makes quantum computing so different from the classical computers we use every day. At the heart of every classical computer are bits, binary digits that can be either 0 or 1. Every app you run, every website you visit, even this video is ultimately just a giant collection of zeros and ones being presented together. But in a quantum computer, we use qubits or quantum bits. Unlike classical bits, they can be both 0 and 1 at the same time. Thanks to a property called superposition, you can think of it like a spinning coin. It's a property called superposition. You can think of it like a spinning coin. It's not just heads or tails while it's spinning. It's sort of both. Another cool thing about qubits is entanglement. When qubits are entangled, the state of one instantly affects the state of another. Even if they are apart, it's like two dices that always show matching numbers no matter how far they're separated. It sounds impossible, but it's real. These quantum properties allow a quantum computer to process an enormous number of possibilities at once. For example, where a classical computer would test each password one by one, a quantum computer could test millions and billions of combinations at once. That's why quantum computing has such a huge potential in this field, like drug discovery, artificial intelligence, climate modeling, and especially cryptography. But there's a certain twist to it. Even though the core of quantum computing is in the quantum, it still needs something to manage, control, and connect to the real world. And here's why digital electronics comes in. And that's what we'll get into next. Now that we understand what quantum computing is all about, let's take a step back and talk about digital electronics. Because, well, quantum computing sounds futuristic, it still relies heavily on classical digital systems to function. So, exactly what is digital electronics? In simple terms, digital electronics is a field of electronics that deals with circuits operating on discrete values which are either zeros or one, just like bits in computing. These values are represented using voltage level. If it is a 1, it's a high voltage. If it's 0, it's low voltage or off. It's the technology behind nearly everything we use today: smartphones, computers, televisions, calculators, you name it. But digital electronics isn't just limited to consumer devices. It's also used in signal processing, error correction, communication system, and more. In the context of quantum computers, digital electronics plays a vital role in controlling qubits, reading their states, sending and receiving signals, and even coding and timing systems. Think of a quantum computer as a high-performance race car. The qubits are like engine, but digital electronics is the steering, brakes, and dashboard. Without it, you can't start the car, control it, or don't know how it's performing. Now, we know that digital electronics is essential for quantum computing and its matter. Let's dive deep and connect to the concepts of digital electronics used in quantum computing. So, how exactly does digital electronics help in the functioning of a quantum computer? The answer lies in the deep integration of classical hardware with quantum mechanics. First, let's take a look at qubit control. Qubits are incredibly delicate and operate at near absolute zero temperatures. To manipulate them, we send extremely precise electrical signals, usually in the form of microwave pulses. These signals are generated using digital to analog converters (DACs) and field programmable gate arrays (FPGAs), which are both core component of digital electronics. Now, these pulses must be controlled with an extreme precision, down to nanoseconds. If the digital signal is even slightly off, the qubit could flip to the wrong state or lose its coherence. Digital electronics is responsible for producing and timing these signals with incredible accuracy. Next comes readout and measurement. Reading the state of a qubit isn't as simple as checking a bit in RAM chip. Quantum measurement is probabilistic and fragile. Specialized electronics are used to amplify and digitize the signal from the qubit so that we can interpret the final state, whether it collapsed into a 0 or 1. Then there's error correction. Because quantum systems are so sensitive to noise and environmental interference, errors are far more common than in the classical computing. To compensate, we need complex error correction schemes. These rely on traditional processors and circuits running in parallel with the quantum system to detect and help correct mistakes in real time. Let's not forget timing and synchronization. In a quantum computer, thousands of signals needs to be synchronized with near-perfect timing. Digital electronics handles this orchestration through precise clock distribution networks and signal routing. Even the cooling systems, often based on cryogenics, are managed using digitally controlled feedback loops. These ensures the entire quantum system stays stable at a few millivolts, just a fraction of a degree above zero, absolute zero. In essence, while the quantum computers process data in a way we have never seen before, it's digital electronics that provides it's the tool, infrastructure, and environment to make all of it possible. It acts as a translator between the classical and quantum world. So you could say that quantum computers can't run without digital electronics. They work like a brain and nervous system in a symbiotic relationship. Now, as we have discussed the power of quantum computers and its high level of processing, there is a threat, which is the encryption and the quantum threat. One of the biggest reasons quantum computing is making headlines isn't just its raw power, it's the threat that it poses to the current encryption systems. Today, most of our digital lives are secured through encryptions. Wherever you are logging into your email, making online purchases, or accessing cloud storage, systems like RSA and ecliptic curve cryptography are widely used to keep our data safe. Now, these quantum methods rely on mathematical problems that are hard to solve for classical computers. For example, the RSA is based on challenge of factoring large prime numbers, a task so difficult that it would take even supercomputers thousands of years to crack strong keys. But here's the twist. A quantum computer using an algorithm called Shor's algorithm can solve these problems exponentially faster. What would take a classical computer 1,000 years, a sufficiently powerful quantum computer might do it in minutes or even hours. This is where the quantum threat comes in. It refers to the idea that once large-scale quantum computers are available, many of our current encryption systems will be obsolete, and it's just not the sole problem for future. There's a concept called store now, decrypt later (SNDL). Many of the huge countries' organizations are using this SNDL because they believe that in the future they will build such quantum computers which will be able to decrypt the encrypted data right now. Now, many attackers today could be collecting encrypted data like confidential emails, financial records, or government communications with the plan to decrypt them in the future. Once quantum technology matures, that's the challenge well quantum computing poses to the humankind. But don't panic yet. The cybersecurity community is well aware of this, and there's an entire field called post-quantum cryptography (PQC) working on developing encryption methods to save quantum computers from breaking into our analogical encryption systems. Still, quantum computing could be a double-edged sword. While it threatens the current security protocols, it also helps build even stronger security through quantum encryption techniques like quantum key distribution, the QKD, which we will shortly talk about in the later part of the video. In short, quantum computing has the potential to change the security landscape completely. It's not about the speed,
So, till
it's
we
about
really discover
redefining
a
what
way to
secure even
adjust
means
the
in this
superposition
digital
of
age.
quantum computers and correctly read the position of quantum computers, no matter in whatever state they are, our data is safe. But what if someone wakes one morning and discovers a method to justify the superposition of the quantum computers? What if there is a way created to read the superposition of the quantum bits? Well, don't worry. Scientists have also found a solution for it, and it's called as quantum cryptography. Quantum cryptography is a method of securing information by using the principles of quantum mechanics. Unlike classical encryption, which relies on complex mathematical problems, quantum cryptography uses the behavior of quantum particles, such as photons, to transmit data in a way that makes eavesdropping detectable. The most well-known technique is quantum key distribution, which is QKD, which allows two parties to share a secret encryption key securely. If a third party tries to intercept the key, the quantum state of the particles change, alerting both parties to the intrusion. This makes quantum cryptography potentially unbreakable by both classical and quantum computers, offering a new level of security for future communications. Now let's discuss how the quantum key distribution in quantum cryptography works. It is a secure method of exchanging encryption keys using the principles of quantum mechanics. The most well-known QKD protocol is BB84, developed by Charles Bennett and Gilles Bazard in 1984. It works by few steps. Number one is photon transmission. A sender sends individual photons to the receiver. Each photon is polarized randomly in one of the two bases. These polarizations represent bits, zeros and ones. Number two is random measurement. For example, the party A measures the incoming photons using randomly chosen bases. Because of quantum mechanics, if he chooses the correct basis, he gets the correct bit. If not, the result is random. Now, number three, public comparison. After transmission, the both parties publicly compare the bases they used. They only keep the bits where their bases matched. This becomes the raw key. The next step is step 4, the error checking. To detect eavesdropping, the both parties compare a small portion of the raw key. If an attacker, an eavesdropper, tried to intercept the photons, the act of measuring would disturb their state, introducing noticeable errors. Number 5, and the final key generation. If the error rate is low, they discard the test bits and use the remaining bits as their secure encryption key. Because of quantum principles like the no cloning theorem and measurement disturbance, any interception attack is detectable, making QKD inherently secure, a huge advantage over classical key exchange methods.
So now, as we have discussed the quantum computing and the high-level role of digital electronics in its functioning, we come to the end of this video. I could go on this video for hours and hours explaining you different topics about digital electronics and its integration with quantum computing, but let's keep this video short for today. Now, as we end this exploration, let's take a moment to reflect. Quantum computing is not just another leap in technology, it's a paradigm shift. With principles like superposition and entanglement, the massive parallelism of qubits, we are entering a new era of computation. But just as it opens door to possibilities in fields like drug discovery, climate modeling, and AI, it also brings a serious challenge, especially in digital security. That's where digital electronics plays a central role. It's the bridge between the classical control systems and the quantum logic, allowing us to build, operate, and scale these indirectly sensitive machines. From error connections to cryogenic electronics, we rely on digital hardware to make quantum computing practical and precise. The future now demands a two-pronged approach, developing quantum computers while simultaneously building quantum-resistant cryptography and organizations like NIST working to define new cryptographic standards. At the same time, quantum cryptography techniques like QKD, the quantum key distribution, may lead us to a new level of information security, one where physics itself guarantees protection. In the upcoming years, we'll see a closer integration of digital electronics with quantum computing, acting a whole new foundation upon which quantum technologies are built, tested, and deployed. So, whether you are a student, developer, a professor, or just a curious person like me, this is the space worth watching, because quantum computing isn't just about the future of technology, it's about the future of trust, privacy, intelligence, and humanity itself. So, thank you for joining me in this journey and hope you enjoyed the video. Thank you.